Check. Hello, hello, hello. Okay. Is anybody having any trouble with this line? David, did you get yours to work?
It doesn't work in the Docker, but it works locally, so.
Work in the Docker. Okay, that's strange. Maybe some, okay. I recommend that you run it within the Docker, but the library should be pretty easy to get. Okay, so I'm going to start. Oh no, don't close tabs. Okay, so this is using this one session from our paper. So the first thing that happens when you run it is that it'll just load some data from a pickle. And so one of the great things about MATLAB is that that it has fairly reliable saving. And I feel like one of the challenges with Python is that it doesn't have fairly reliable saving. So you'll find that pickle formats they change, and sometimes if you save something with one pickle format, it won't open with another version of the pickle library. So we haven't solved that problem. But hopefully, since you guys are all roughly on the same version of pickle, it should all work. So there's 3 variables of interest in the data that is included in this Git archive. So there's position data that was captured by video tracking or whatever. There's spike train data, and then there's some markers of where these ripple events are, which we call population burst events. And we can talk more offline about how to detect those sorts of things, and there's some routines to do that, but I'm not going to include that in this tutorial. Okay, so these are objects in this library that we built for spike train analysis stuff, and they sort of tell you interesting things about them when you print them or just sort of look at them. And so in this case, this is a 2-dimensional variable that has some time duration, and we can plot it. And what we see is this sort of thing here. So this is very common when you look at data that's recorded from rats where they're head tracked, because when they turn around, their head sort of swings off over the end of the track. In this case, the track was lined up pretty nicely with the maze, and so in 2-dimensional space, this is fairly constrained. Sometimes you'll see things that are at an angle or somehow otherwise annoying. Okay, so one of the key challenges that I feel like probably every tutorial sort of operates on is herding time, right? Time is always recorded in different sorts of ways. It's a problem with any sort of a data, any data where things are sampled at different rates or with different instruments. And so one of the things that we've sort of built into this library is this concept of temporal support. So you can look at an object and you can ask over what time period is their data. So there's a master clock. That master clock recorded data over a much larger period of time. And in this case, this particular position data happened in these seconds. So 1250 seconds through 2580 seconds. Okay. So we can pick a smaller amount of time and create our own little time window. So it's called, which we call an epoch or something like that. So in this case, let's look at what happened between 1300 seconds and 1320 seconds. So we can create this little thing, and then we can sub-sample or window our position data just during that period and plot it on top of the overall position data, and we see that that's like one run of the rat in this black. So if that makes sense. So that the key line is this one here, where we're bracketing over time. So almost all of the data that we work on is temporal, and so the first dimension of almost every object, if you wanted to use square bracket indexing, is going to be time, and so you can window time. And you'll see that sort of temporal filtering is really useful when you're trying to look at different kinds of events, or you're partitioning your experiment into different things. Okay, so two-dimensional data is not as easy to work with as one-dimensional data. So to convert this into 1D, we're going to do 2 things. So the first thing to do is to smooth it. And so built into this position structure is a smoothing function. So let's just smooth it with 3 different sigmas. And these are given in time, right? So this is 0 seconds, 0.1 seconds, 0.3 seconds. And what you'll see when we do this is that they get smoother and smoother as expected. Okay. So, but what we want is we want a one-dimensional version of this instead of a two-dimensional version. And the easiest way to get a one-dimensional thing from something that's close to one-dimensional is to use principal components analysis. So, so let's grab PCA from scikit-learn, and then what we could do is we could just principal component transform our position data. Okay, so this is the this underscore y data is the two-dimensional data of the oh, that's actually described here. So this is the raw data that underlies this object. So whenever you want to access things that are the raw data, like the matrices, like you would have in MATLAB, underscore y data is the thing that we want. Okay, so let's run this. And then now what we can do is we can project our one-dimensional thing, which is this x linear, back into two-dimensional space. So that's this inverse transform, and then plot it on top of the raw data. And so what we see is that all of our trajectories are on this line, and the line is almost horizontal. I think if you squint, there's maybe some slight angle, and so that maybe there's some marginal utility of using this versus just using the x-dimensional data. Okay, is everybody following me so far? So we did a little bit of dimensionality reduction from 2D to 1D in order to have position data in one dimension. And then now just for ease of operation, let's get rid of the units. So we'll go away from centimeters that are in some sort of arbitrary place to just make this the percentage of the track. So this track is 150 centimeters long or so. So each percent is about 1.5 centimeters. Okay, so now here's this one-dimensional thing that's just a NumPy vector, and we'll convert it back into a NumPy object just by calling this constructor function. And then so here now we can compare those two objects. So one is a two-dimensional object, one is a one-dimensional object. And we can plot it, and what we'll see is basically that the rat sits still for a while when you plop him down, and then he starts running back and forth, and he's getting chocolate milk at each end. And then, so he's down here for a while, drinking his chocolate milk, looking at the world, scratching himself. At times he decides to take breaks, like on the track, and then he starts running again. And then at some point he just sort of gets bored, and at this point, if you were in these sorts of experiments, you're thinking to yourself, well, is he bored? Maybe we should stop the experiment. No, I'll let it go on a little bit longer. And then he starts running again. You get excited, and then no, actually, it's done. So this is the. I guess I presumably humans do this too. You think that they'll keep going, and then at some point they just give up, and you try to I don't know. You can't really. Can you offer them more money halfway through the experiment? Please keep going. Please try. I don't know. Never having done human experiments. Okay, so next thing, let's take a look at the spikes. So when we do these experiments, we're putting electrodes into the brain, and the signals that we see are voltage signals, and they're not just spikes. They're voltage. There's spike action potentials, extracellular action potentials that are in this milieu of local field potential and noise and junk. And so the first step in the sort of data processing process is to take that raw continuous signal and pull out the times where we see action potentials. And then usually there's a second step which involves matching action potentials from individual neurons to themselves based on the shape of their waveform. So usually you see some sort of thing that looks like this, and maybe you see another one that looks like this, and these are usually consistent, and so you can say that's one neuron, that's another neuron, and so on. Okay, so when you end up doing all of that, at the end of it, what you have is you have all of the times where you saw this thing, and all the times where you saw this thing, and so on. And so you have a structure which is not really an array, because the number of spikes from each neuron is different, right? So if it was a matrix, and you might imagine that there would be some number of neurons and some number of spikes, but it's not the same number of spikes, right? So this is slightly different than a voxel signal. If you think about a voxel signal, you have voxels and signals from every voxel at every time, but here you don't have a signal from every neuron at every time. So in a minute, we'll convert it into something that is like that, but just for a minute, we can look and see that the number of spikes that we see from each of the neurons that are in this data set is pretty variable. Okay, so there's this support again, that's embedded into this structure that tells you what time it's recorded over. And a support object always has a duration. So in this case, the duration is probably something like, 22 minutes. So we can just so this is, Python is weird, right? When you look at an object like this, it actually calls like a print function. So there's actually a raw data number that is encoded into this that is there for you to divide by, but this just pretty prints this in terms of minutes and seconds. So we can do this where we can take the number of spikes, which is this array, and we can divide it by this amount of time, and then we get some firing rate. So what we see is that our neurons have some average set of firing rates. Okay, so let's just take a look at the spike data a little bit more. There's this convenience function called Raster Plot. This, if you ever look at spiking data, people give talks, it often looks something like this. So this is all the neural data for this talk. It's not organized in any nice way. But we'll organize it here as we go along. But this is just basically where we're starting. I think one of the things that's interesting is that if you just look at this and you squint, you can sort of see there seems to be something that's happening periodically. And if you remember where the running was, it's happening right about the same time. So you can already sort of see the running embedded here into the spiking activity. Okay, so let's try to, one of the things that we need to do in order to do subsequent analyses is we need to figure out when the rat was running. So the easiest way to do that is to just look at their velocity. Yeah?
Yesterday when we were doing some of the connectivity tutorials, we spent a long time talking about, like, should you be z-scoring and things like that. And
Yeah.
in this case, I assume something similar could be true, where each site that you're recording from has its own resting voltage.
Uh-huh.
And so I was just wondering if you could comment on whether you think it's important here to normalize the data or whether it's important to not normalize the data.
Yeah, so when we get to decoding, the firing rate of a neuron will have some impact on the way that it gets weighted into the joint distribution for position. But it's unclear to me that, yeah, so it's complicated. But I think there's no reason to believe that a neuron that has a higher modulated firing rate is not actually more informative. So for example, if one neuron fires 1 spike and one neuron fires 10 spikes at their peak, we could think about this in 2 ways. We could say, well, this is a problem because when we combine that information, the neuron that can range between 0 and 10 will give us more information than the neuron that can range between 0 and 1. So maybe we should truncate the 0 to 10 down. But I don't think there's any really good reason to do that. I think it probably is just the case that neurons that have larger firing rate modulations are really more informative. And so z-scoring is a way of trying to make your things equally informative. And so in this case, I think we don't necessarily want to do that. Okay, so if you've ever tried to just calculate a derivative, so you probably have used like MATLAB diff. So MATLAB diff does some weird things in terms of right? So the diff of a vector is 1 smaller than the vector itself, right? Okay, right. So the naive way of calculating speed would be, let's take the position and let's take the diff, right? And then maybe we could smooth that because we want it to be slightly better. But there's actually some nice built-in in NumPy. There's some nice better derivative functions that will actually give you the derivative that's centered on a point. So it uses the points before and after a point to calculate the derivative as opposed to just the points in the middle. And so that's wrapped up in this convenience function here, dx dt. So this is giving us the speed. And then there's a second convenience function that looks at that speed and finds places where, so let's do this. Who knows whether that was a mistake? Oh man, no, stop. Well. Okay, I just killed my kernel. So anyway, so let's, where was I? Dead kernel. So if this ever works, then what we'll see is we'll see something that looks like this. So the way that we want to find the periods when the animal is running is we want to look for spots where this goes over some threshold, but probably the bouts of running have started below that. And so we actually have built in a little function. Python for the win. How many of you are Python experts? That's awesome. Nobody. Okay, so let me just tell you something that I figured out that's sort of fun. If you plot a column, then it thinks that you want to plot like a bunch of individual objects. Like if you plot a row, then it thinks you want to plot a line. And so I did this like 80,000 point column, and so it's like, oh, let me plot 80,000 individual like one unit lines. Hell, but it worked. So let's do it this way instead. There we go. So what this function does is we're gonna look for some threshold, and we're gonna identify bouts of running just by periods where it crosses the threshold. We could actually make the second thing a different number, in which case we would define the bout, and then we would work our way down around the edges to a lower speed to find out when it started. Okay, so. This says that the animal was running for a total of 3 minutes of the 20 minutes that they were on the track. Okay, and so now we can do, for example, we can ask what the average firing rates of the neurons are while the animal's running. Okay, and in the next line we can plot these running bouts, and they just automatically get encoded in a different color. So these are the periods when the animal is running, and these are the periods when the animal is still. And there's some nice features. So if any of you are ever going to do this, where you really care about thinking about different data structures that allow you to think about time in a nice way, it's really nice to be able to do things like invert a time frame and say, okay, I want all these periods, or I want all the things that are not these periods. And so that's one of the things that we've spent a lot of time thinking about, probably to our detriment. Okay, so now here's all the data where the periods when the animal's color is running is colored in, and we can zoom in on a smaller section and see spikes that happen during running and spikes that happen while the animal is still. All right, so let me spend a few minutes talking about sort of the traditional way that we would do place cell analysis. So the first thing when we think about a place cell is that we think about what its place field is. So what is a place field? Okay, well, a place field is the area where a neuron is active, or another way of thinking about it is it's the spatial firing rate map of a place cell. So how do we calculate that? So let's start with just looking at spikes that happen while the rat is running. So now in this little structure here, we have the spike trains that happen when the rat is running. So let's bin spikes. Binning is the easiest way to start. There's ways of doing place field estimation that don't rely on binning, but binning just makes life easier. So in this case, let's bin them. Let's bin them into 1/8 of second bins. An 1/8 of a second is a theta cycle, and so it sort of is a nice easy number. Okay, so now we've binned all of our spikes into these 1/8 of second time bins. Okay, so I'm going to go through this with one neuron just a little bit quickly, but then it's actually just a single function a little bit lower on that you'll see makes nice place fields. So the first thing is, let's look at the spikes that are coming from a neuron. So I just picked a neuron. This is neuron 26. Here's the position as a function of time, and here's the spikes. And now remember, I started out with the spikes that happened when the rat was running. If I had done this for all of the spikes, then you'd see something slightly different. So we can do this. Oh, no, not that. This. So now you see that this neuron actually is it's also firing when the animal is not running, and it's at times when the rat is, mainly times when the rat is sitting still, but there's also some times in here where he's slowed down. So when we do place cell analysis, we think, okay, well, we don't want to include ripples or periods when there's other stuff going on, when the animal's not in sort of the place cell state. So we want to get rid of that and just look at the periods. This is why we restrict place cell analysis to periods when animals are running. And the unfortunate thing about that is that there are pyramidal cells that produce place cell activity when the animal is sitting still, and we just typically ignore them. It's just in the last 2 or 3 years that people have really started digging into the neurons that are active in the hippocampus when animals are not moving. And it's a whole sort of separate network that's actually pretty interesting. Okay, so naively, we could just bin these spikes by space and call that a firing rate map. The problem is that the animal spends a lot more time in these places and in these places than in the middle. And so really what we want to do is we want to divide the number of times that there was a spike in a spatial bin by the number of times that the rat was in that spatial bin. So there's actually 2 sets of binning that we want to do. One is we want to bin the behavior, and then the second is that we want to bin the spikes. So we'll do this here in the next couple of lines. So this is just going to calculate a histogram of the behavior. And there's a little trick here where we just made some bins. We're going to bin from 0 to 150 bins. And we want to call histogram, but what we're going to do is we're actually going to find the positions from the position data that happened for all of our spikes. We're using our spike timing time, our spike bins as our time base. And so we're going to calculate the position at every spike bin time center. So these are the centers of the temporal bins of the spiking. We'll calculate the position and then get a occupancy histogram for that. So this says that over the period of this behavior, the animal spent a lot of times at the ends and a little less time in the middle. Okay. Then we can do the same thing for the spikes. So we'll just add up all of the times when all of the places where a spike fell by going through all of the times and then just adding a tick to the times when the spike was in a certain place. And so then we end up with something like this. It's the raw rate map. And the last thing we'll do is to divide the two. So divide the rate by the occupancy. Okay. So all of this is actually captured into this one nice function. And that concept of the tuning curve has some built-in convenience things where we can like do ordering. And so when we do this all, we end up with something that looks like this for all of the neurons in our data. So when we look at these, you can see that there's some that have very nice high firing rates that are very spatial. There's some that basically are never active on the track. There's some that have very, very little spatial modulation. So really what this is demonstrating is that we have some neurons that are place cells and some neurons that are not. And I talked about that in my talk this morning to a fairly great extent. So it's not important to talk about again. But the thing that we want to do for normal replay analysis is we would want to pull out neurons which were just place cells. And so a way to do that is to ask that they have a minimum peak firing rate, that they don't have, and they have a ratio between their minimum and their maximum, which is reasonable, and that their average firing rate is smaller than some amount. So basically, if you have a neuron that is not a place cell but is very active, it's probably an interneuron. It will have a high firing rate over the whole environment, and its ratio of maximum to minimum will be small. So down here, we're just going to find the place cells by doing that, and then plot the things that are identified as place cells. And then there's some stuff that we can do in terms of decoding that I'm just going to skip over for the sake of time. Just wanted to show this last thing. So when we take our place cells and our non-place cells, and we can order the place cells by where their place fields are, then we can end up with something that looks like this, which barely fits on my screen. But now this is showing the times of neurons that we've, of course, identified as place cells just with the simple criteria. During running, they sort of are active. And then there's another cohort of neurons that are also active. We're getting some spikes from them, but they don't seem to be spatial. So when you think about the hippocampus, keep this in mind, right? There are these spikes from these neurons that are not place cells that are happening. And probably that's some of the mystery. Okay, so let's skip ahead. I think let me quickly talk about decoding. So this really, I should have put this in the notebook because LaTeX will be cleaner than my handwriting. But it's not necessary. So how many of you have done some sort of decoding before? Okay, a few of you, okay. So the idea behind decoding is that we have something, right, that thing that we just drew, which is the firing rate as a function of position. So this is x, and this is firing rate. For neurons, for many decoding analysis, so in order to do decoding, that implies that you're doing something with statistics, some sort of probabilistic model. You can do estimation without probabilistic models, but when you're doing decoding, it implies that you have a probabilistic model. So a lot of times, you may be using a Gaussian distribution. For spikes, we almost always use a Poisson distribution. So that means that for one of these time bins, what we're saying is that the probability of seeing k spikes at position x, so we'll say the probability of k given x is equal to even minus lambda x to the k over k factorial. So there's some equation. The shape of this equation is not critical, but there are a couple things that are important to notice. OK, so the first thing to notice is that things are weird in the case where your rate, so OK, for those of you who may want to do this one day, if your rate is 0, like literally 0, like exactly 0, then, and you've estimated it as 0 using some training data, and then you have that data that you're testing or decoding, and you observe a spike in a period where you expect the rate to be 0, then you have this thing where here's, so lambda is our rate, so we have now 0 to the 1 power, and that thing is not well defined. And so we usually hack our probability distribution by enforcing some minimum rate. OK, so this is the probability for one neuron if to observe some number of spikes, k spikes, in position x. So now if we observe k spikes and we want to decide what position the animal's in, we can ask what x maximizes this probability. So now we can take this thing and treat it now not as a function of the number of spikes, k, but as a function of this variable x. So we can actually think of this lambda as a function of x. And we can ask what x maximizes that function. In the case of this probability distribution, it's pretty easy, right? It's going to be, so if we observe a k that is large, then it's going to be somewhere here. And if we observe a k that is small, then the most likely positions would be here on the sides. So what this says is that if you just have one place cell, then you can't tell where you are with very high accuracy. So the interesting thing about decoding is that you now have a second, or not a second, but many place cells with different curves. And then the trick to decoding is understanding how to combine the data from each of these things. And so now what we can do is we can just multiply the probabilities for every position together. So we have the probability for neuron 1 that we saw k, that like it spikes neuron 1 given this position x. Probability of neuron 2. Probability of neuron 3. OK. So Bayes' rule then says that what we can say is that that this thing, which is the joint probability of n1, n2, and n3 given x, if they're independent, is equal to the probability of x given this thing times the probability of just the neurons divided by the probability of just x. OK, so normally these two things end up being, so this we assume to be uniform. Well, this doesn't matter if we're trying to find the x that maximizes this. So we can ignore this term. And we assume that our prior probability is uniform. And so this also doesn't matter. So in the end, this thing and this thing are approximately the same thing. And so we can write the product of these three probabilities down, and that becomes some big function of the number of spikes we see in 1, in 2, in 3, and x. And then we can maximize this over x. So we can say max over x. Okay, so that's lots of math. It's super complicated, like to write down, but it's actually really trivial in practice. What this means in practice is that when we observe some number of spikes from every neuron. So from neuron 1, we see 1 spike. From neuron 2, we see, say, 3 spikes. And from neuron, this is neuron 1, so we actually saw 10 spikes. Neuron 3, we saw 0 spikes. Neuron 3, we saw 2 spikes. So we can actually write down for each of these what the probability is for our bin space and take the product of those things. So using that formula that I just wrote down. So now we get something. So we're going to multiply all these together. And actually, we don't multiply them all together. We take the log and we add them together. And then we get something which is a function of position. And this then is the decoded or a posteriori probability of the animal being in each position. In this case, it's probably going to look something like this will be very high, this is smaller, and these are sort of empty. And that's just by combining each of these vectors by taking one big product. And there's even more efficient ways of calculating it that you can get. So yes, all that is to say we can decode, and I just want to show you guys what it looks like when we decode some ripples. So I showed you this earlier. So this is actually all of the ripples decoded, and this is just one. So let's look at this one. Okay, so this thing that I just described is this one column. So we've calculated that the maximum probability, given that we've seen spikes from 1, 2, 3, 4, 5 neurons, 6 neurons, is right here. And then similarly here, when we see spikes from this many spikes, so in this case there's 2 spikes from that neuron, 3 spikes from that neuron, or sorry, there's 1, 1, 3. That corresponds to a high probability in this position, a low probability in the other position. So maybe I want to go do some HMM stuff in the last 2 minutes. So really quickly, I went over this super fast, so I feel a little bit bad. But if you're interested in decoding stuff, I'm happy to talk to you at some point in the future. Okay, and don't run this cell. Yes, this is the one that takes forever. So if you're really interested in replay, then you can run that cell. But that's the one that you'll be sad, and then you'll have to kill your kernel, and you'll have to restart the whole thing. Okay. So HMMs.
Sorry, just quickly, what was the step after adding the month?
Well, so to generate those rate maps, there was no step.
Okay.
That is just what it is. It's technically not true, right? So technically, for it to be a true probability density, it should sum to 1. And so you should exponentiate it and then divide by the sum of the things to get an actual probability density. But for proportion, this is, yeah. So here's a question. I understand that this cell may have problems. Can somebody try running this cell, the one that says import nelpy.hmmutils? Yes? It worked? Okay, good. Huh, so Matt was just special. Okay, awesome. So what I'm going to go through right now is making not what I talked about. So we're just going to make a hidden Markov model from the spiking that happens when the animal is running. So the place it will start is by combining. So I mentioned that the spikes happen at particular times, right? So we bend the spikes in order to calculate the tuning curves. We bend the spikes in order to decode, and we want to bend the spikes in order to do HMMs. So when we do this, then we end up back in a situation where we're like voxels in fMRI again, where we have data that looks something like this, where this is n is the number of neurons and t is the time. Okay. There's one subtlety here, which these structures are hiding from you. So if I look at if we actually just look at this structure, it actually has 84 segments. So this is not one big continuous thing. It's actually split up into 84 discrete segments that correspond to discrete times when the animal was running. And that's important because when you train a hidden Markov model, there's sort of two ways that you can do it. You can train it on one big sequence of data, in which case you will end up with an incomplete estimate of one of the key parameters. And another way is that you can train it on many sequences of data. And the key parameter that you miss out on when you train it on one big sequence is the initial state probability. So in my talk, I showed you guys a transition matrix, and I showed you a mapping between states and observations, like the firing rate matrix. But there's also a third thing, which is the initial state probabilities. And a true description of a model says you have to know where the states, where the chain of Markov states starts. So if you don't have that, then you can just assume that it's uniform. But if you have many sequences, if you are actually really interested in trying to understand the dynamics of the sequences, then you want to train them as individual sequences, and then that way what you can find is this probability of these initial states, which won't be uniform and will actually tell you something potentially interesting about your data. So first thing is we'll split into training and test data. And then the next thing is we're just going to run this function. And the function is Ihmmphit. And so what this is doing is that this is applying this expectation maximization algorithm. And the way that that works is that it calculates a score. So it initializes all of the three parameters, the initial states, the transitions, and the observations, calculates a score for that, and then it moves in a gradient to improve the score by changing the parameters. So it maximizes the parameters. It calculates the scores using the new parameters. Then using those new parameters, it finds the states for every piece of data. Then it uses those state estimates to calculate new parameters, and it iterates. And usually the convergence is reasonably fast. OK, so the next thing to show is what I said about ordering. So when we look at the state transition matrix that gets returned by EM, we see that there's a nice diagonal, but all of the data is not clumped on the off diagonals like it was when I showed you. So the next thing that so this is just sort of what you would get after you ran EM. But you can sort these states, and there's just a very simple way of sorting them for display, and this may be of interest to you guys. So you can just start at one state, and then find the state that has the maximum transition probability, and make that one your next one. And then from that state, find the one that has the maximum state transition, and make that your next one. You can just do that greedily, and then you end up with something that looks sort of diagonal-ish. OK, so you guys just trained an HMM. Awesome. Or if you hit run on that cell. And you can look at the transition matrix. You can look at the observation probabilities. And here we'll do some live stuff that I'm not sure what will happen. We can look at the initial state probabilities too. They're called start prob. So there's some sort of non-uniformity in which states are likely to be first. It's interesting. We haven't explored this at all in our data. There probably is something interesting there. Okay, so I showed you guys these latent state fields where we estimated fields for the data. And so the way that worked was that the first thing was to estimate the states that correspond to some left out data. So if we look here, here's our well, let's plot them and then we'll come back. So here's our position data during whoa, stop. Here's our position data during this task. This is just a bunch of stuff to make sure that we have our position data binned nicely. That's this extern thing. And then this is calculating the rate map of this data. And that's just using the, sorry, this is important. So this function right here, fit external. So what this is doing is it's calculating the states that correspond to this data, and then it's fitting them to this external thing, which is just position. And the way that it's doing that is it's just averaging this, just like we did for the receptive fields. So if you guys, if you're interested in that, you can dig into this code. But then we can just plot what these look like, and what we find is something just like I showed you in the talk. So there's an example just of looking at the state decoding. And then position decoding from this. So the first thing is that this function here scores all of the test samples. So that basically means what it's calculating is it's calculating the posterior distribution for every time bin in the data. So this is what this is. So we could look at other ones. So these will all be state sequences of some kind or another. Some of them are ugly, some of them are pretty. And then when we decode, what we're doing is we're taking this position mapping and we're mapping these two states back to back to position data. So now when we do this, this says, okay, these states correspond to positions early on in the track. All right. So this is sort of the end of what I wanted to talk about. This is the one thing I haven't shown you guys here is the replay detection by shuffling, but we can talk about that offline. But yeah.
So you trained the HMM to know about something that has transition states, and
Yes.
you got data that has transition states.
So let's dig into this example just quickly. So I think this will work. Okay, I can't do that. So there should be some way for me to plot one of these examples. So these are our test binned sequences, right? And they're just spikes. So they're spikes that have been binned, so smoothed over time, right? And then when we call this function, what it's doing is it's estimating these state sequences from those.
But
Yeah.
I guess what I'm interested in is that the data that you've selected
Yeah.
has known replay events in it. But what if you gave the trained HMM data that didn't have these sequential events? Would it still try
Yes.
to find?
Yes. 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 Yeah, I can't do this live, but yeah. So we could we could do like a random number generator, and then feed that in, and it will do its best to find something that fits to.
So it can't appropriately
Yeah, it will always find something. The probability will be small. So it will give a number, and that number, so for a given event, there is this posterior, which is showing you a probability where it has to sum to 1. But then there's also associated with that a score, which is, I think, commented out here. So I believe that this returns the score as well. Yes. Which will vary from one event to another. So it's important. An important caveat. So there's some range of numbers, right? So some events are in log space, log probability space, are very, very small. So they're very unlikely given the model. But there's something weird, right? Which is that every time you add more data, you add more probability. When you add more probability, you're always multiplying by something else that's less than 1. So your probability always gets smaller. So there's something weird where you could have a really, really long sequence that was almost perfectly matched to the model, but it would have low probability just because it was comprised of something that was very long. So there's some sort of normalization by length that has to be done. And so then in the end, this is why we ended up normalizing by shuffled versions of the data to try to understand how different something was than a shuffled version of the data.
So even if it finds structure in noise, then the shuffled version shouldn't be that different, so that tells you that it was not the structure.
Exactly. Yeah. It's frustrating. I really would like, because I like statistics, I would like it to not rely on having to shuffle something to figure out what truth was.
If it's unsupervised, that's okay, I guess. Yeah. How otherwise would you know?
Well, there may be, so there's some theory about how probability should decrease with the increasing length that would say that you should scale by dividing by the number of bins. And there's probably also something else about just the structure of the neurons that would give you some sort of prior onto how your probability should look. So I feel like that there may be some sort of analytical solution, but we haven't found it yet. Yeah.
The posterior itself can't do that?
So that is the posterior, and so this is the problem. So posterior will monotonically decrease with increasing data in every dimension, which is not ideal. So if you're only dealing with sequences that are of the same length, then there's probably some reasonable comparison. Yeah. All right. So HMMs. This library it's very fast. So training an HMM is really quick. I mean, this is 100 neurons by hundreds of time bins. So if you guys want to try this on some other sort of data, I would love to help you sort of implement that. It should be pretty easy. And there are some convenience functions built in for shuffling as well, so that can make your life easy potentially as well. Yeah.
So every time we run, if we keep a state, the number of states the same.
Yeah.
If every time you run it, it would give you a slightly different
Yes.
combination.
Yes.
How do you know which one is right? Should you do 5,000 times to figure out and do some permutation or something like that to figure out what is the most likely one?
Yeah. So when expectation maximization of HMM with these sorts of observations will yield optimization surface that's not convex, meaning that it is possible that depending on your initialization values, you may get something that's better or worse, right? So in the overall likelihood of your training data, which is a problem. And so it's probably a good idea to randomly initialize and then train multiple times. However, what we found is that usually doesn't make that much of a difference if the training data is large enough that things seem to converge. Also, I just picked k, there's a line up there where it says k equals 30. And we could have done the whole thing for k equals 100, and it would have all just it would have still given us something. So understanding the right number of states. So the number of states is, whoa, it didn't like that. So apparently a number of states equal 1,000 causes a problem. I don't know why, I'll have to see. It takes longer to train things with more states, but what we found at least was that it seemed like things were relatively insensitive to that, and the things that we were looking at, like replay or how we were mapping back to the state space. Okay, but so while this is running, I just want to give you guys like big picture thoughts. You train in HMM, so you do unsupervised learning on some data. You think it has sequences in it. And so you get back these latent state sequences, or latent states, right? So now you're decoding your data, you get states. As I think about it, there's basically just a few questions that you can really ask, a few pieces of knowledge that I can give you. So one would be around the question of what do those states represent? And so in our case, we sort of knew that the states would represent position, and so we were just sort of trying to figure out ways of verifying that they were representing position. The way we did that was we took data that was recorded in sort of a different context, meaning running as opposed to still, decoded it, and then tried to match it up with the variable that we were interested in. So we decoded and paired it with some external variable to see whether there was tuning relative to that external variable of our states. So the whole point of that was just to try to find out, what do the states mean? So if you think that there's some latent process going on, you don't know what the latent process is, then that's sort of an interesting sort of analytical framework. The other thing is, the other reason to do this is if you really believe that there's some sort of interesting variability, state dependence, that is going on in your data, and you really need an automated way of finding out times just from your data when whatever this broader state thing is happening. So then decoding states can be useful, because then you can say, for example, a person is attentive at this point, or a person is inattentive at this point, or the rat is running at this point, the rat is not running at this point, in a way that you can estimate that from your neural data as opposed to needing some sort of external marker to do that, which can be very valuable when if you don't have the external marker that's describing that underlying process. So I feel like, in my mind, those are sort of the two spaces where HMMs are interesting. So or really latent state analysis is interesting. When you feel like that there's some sort of interesting latent states that you want to try to understand better, and where you're going to use those as a way of just understanding your data better. You sort of know that they're there, and you need an automated way of detecting them. So the process is very similar at the beginning, you're training, but then the process afterwards is a little bit different. In one case, you're really sort of exploring what the thing is that you found. And in the other, you're just using the model that you've built as a way of segmenting your data. So I think that HMMs are very useful in both cases, but sort of have different differential utility. If you just need to distinguish a few states, it's almost trivial to set up and run, and if it can be reliable, that can just be really valuable. If you're trying to distinguish a larger state space, then it really is an interesting challenge to try to figure out how to explore that. I think the last thing is specifically sequences, where you're looking at and you're trying to find sequences of things, and you want to figure out whether what you're seeing is really sequential or not. And that's where the sort of mixing between the model scores and some sort of shuffle thing might come in handy. And but I feel like that's sort of a very specific case where people are very specifically focused on sequential information. Okay, that's all I have to talk about. There's actually there's a number of notebooks. There's notebooks that for Nelpy. There's notebooks for the hidden Markov model stuff specifically that are on just another repository that I think is linked at the top of this one. So feel free to play around with those, or come talk to me if you have questions. Okay, thanks guys.